Hi people, when you see a beam of light, do you think of it as a light wave or do you think of it as a stream of particles? Physicists have been thinking of this for a long time. To cut a long story short, at first, Huygens told everyone that light is a wave. But then, Isaac Newton told everyone that light is a stream of particles. So for about 100 years, everyone believed that light is a stream of particles. Then Thomas Young showed everyone the double-slit interference pattern. And so for about 100 years, everybody believed that light is a wave. Then 100 years later, Einstein used the photoelectric effect to convince everyone that light is after all a stream of particles. So what is light? Is it a wave or a stream of particles? Before we answer this question, let's figure out what is the photoelectric effect first. So we start with a piece of matter and then we shine a beam of light on it. Then we notice some emission. Turns out these are negatively charged particles and turns out they are electrons. Since these electrons seem to be liberated by this beam of light, they are called photoelectrons. And this phenomenon is called the photoelectric effect. Now let me make it clear. Photoelectrons are just electrons. They have a mass of 9.11 times 10 to the power negative 31 kilogram. They have the charge of 1.60 times 10 to the power negative 19 coulombs. They are electrons, but they are given this fanciful name, photoelectrons, simply because they originated from the photoelectric effect. So as a phenomenon, the photoelectric effect is quite interesting, but it was nothing mind-blowing, groundbreaking or whatever. Everyone knew that a piece of matter contains lots of mobile electrons, the seas of electrons bound to the positively charged metallic lattice. What the beam of light provides is energy. As these electrons absorb the energy from the light, some of them will be energetic enough to break free, and so they escape as photoelectrons. So as a phenomenon, the photoelectric effect has a very simple explanation. But then it wouldn't be physics if we do not make measurements. And two measurements in particular suggested to everyone that something is not quite right. And those two quantities are the rate of emission and the speed of emission. They look similar, don't they? But they're different, yeah? So look here. These are two photoelectric emissions. One illustrates a high rate of emission and the other one illustrates a high speed of emission. Replay the video if you need more time to make your decision, but I want you to try to guess which one has a high rate of emission and which one has a high speed of emission. Alright, I'm going to continue now. Now, when we say rate, we mean the number of photoelectrons per unit time. Looking at this one, you can literally count the rate of emission. Let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whereas this one, 1, 2, 3. Yeah? So can you see this one has a high rate of emission. The number of photoelectrons leaving the matter is higher. And when we say speed, we refer to the kinetic energy at which the photoelectrons are liberated. So can you see this one goes whee? They travel at quite a high speed, whereas this one, the speed is much lower. So this has a high speed of emission. If you want an analogy, a high rate would be like the human flow during a mass walk. So the number of people crossing a line here is pretty high, even though all of them are traveling at a low speed. They're just walking. Compare this to the marathon. So the number of people crossing the line is very low, but their KE, the speed at which they travel, is much higher. So how do we measure the rate and speed of photoelectric emission? I feel a bit hungry now. We'll continue in the next video, alright? Ta-ta!